This is Lab 4, Optical Beam Collimation and Testing Radius of Curvature. I'm Nathan Isham.
I'm Alan Ye.
I'm Stephanie Wells.
So the objective of the lab is to make wavefront measurements of the collimated beams. So we construct the Capillarian telescope to expand the beam size so it can completely fill the shear plate. So we have a microscope objective with numerical aperture of 0.35 and a wave focal length of 8 millimeters. We have a spatial filter with a size of 25 microns to provide a clean Gaussian beam profile and block the noise. We also have a collimation lens. So to get the expansion ratio, we need to use the size of the shear plate and the beam waist. And ideally, it has to be 62.5. And then using that ratio, we can find out the focal length of the collimation lens to be 500 millimeters. However, in the lab, the only available focal lengths of the lenses are 300 and 800 millimeters. So we decided to go with the 300 millimeters lens, which gives us the actual expansion ratio of 37.5. So using a lens with a smaller focal length will give us smaller collimated beams, which makes it a little bit harder to measure the shear distance later on. To best reduce the aberration, you want the curved side of the lens to face the shear plate, so you can get a shape factor of -1. So if you do it the other way around, you're going to get fringes to be curved and not straight. So in this lab, we use a wedge shear plate to test the collimation of two beams. So three parameters we can measure is the shear distance, the fringe orientation, and the fringe spacing. So the separation of two beams in y direction depends on the refractive index of the plate and the wedge angle. As for the separation in x-axis, depends on the shear distance. So by measuring all the parameters, we can use this equation to determine the wavefront curvature.
So here we have our Capillarian beam expander with our collimation lens of a focal length of 300 millimeters. After our expander, we placed an aperture that basically stops down our beam to clean up the beam profile, since that's what we're interested in seeing in our shear plate. So on our shear plate, it's actually a wedge shear plate, and this allows us to see an interference pattern on the screen because of a different optical path length of the incoming wavefront. We placed a test lens in front of, or in between our expander and our shear plate, and then we were able to see the profile. So our shear plate allows us to measure the wavefront of different optical elements, and we can actually physically measure our fringe orientation, our shear distance, and our fringe spacing. From this, we can actually calculate the radius of curvature of these wavefronts and find the focal lengths of the optical elements that we're taking a look at. We also were able to measure the radius of curvature for a mirror by turning our shear plate 180 degrees and placing a mirror on the back side of the shear plate. For this, we were able to calculate our radius of curvature to be about 48 to 59 meters.
So coming out of the shear plate, we have a collimated beam. This means that we have a plane parallel wavefront. We will send that plane parallel wavefront through a reference lens to focus it down to a point. To find the radius of curvature of our test mirror, we will place it in the beam path and first try to find the close position. We will know that we have reached the position of the back focal length of the lens when the retroreflected beam goes back through the reference lens and produces straight fringes, meaning it's recollimated the beam. We will then push the mirror back to a secondary position, and there should be a position back behind the first position of where the radius of curvature of the wavefront will match the mirror, causing it to return to the reference lens to be recollimated and show straight fringes again. The distance between these two positions will be the radius curvature of the mirror, which we found to be 201 millimeters. Right now we are at the rear position, and as you can see we have straight fringes. We will now move to the closer position. And as you can see, at the close position we return to straight fringes again.